Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Okay, now I'm turning to another important aspect of the mechanics aspect of the or macroscopic aspect of deformation. See, when we say that the dislocation density is increased in the material, and then we talked about how the material behavior get influenced by this and so on. So, what is its influence on the macroscopic strain? See, ultimately, when the strain, the dislocation produces a shear strain, right, in a very localized manner. Suppose if you consider all the displacement produced by each dislocation in this material, ultimately they should contribute to the total strain or a macroscopic strain. So I just want to connect that aspect through this slide. So look at this unit or crystallite. It is slipped. You can see the multiple slip line. The whole crystal is slipped. It is the meaning of this kind of a diagram now. It is a shear, a complete shear, and this is the height is h and the displacement is delta, and the dimension here is z, the length is z, and the shear force is applied in these two directions. The relationship between macroscopic shear and a dislocation transit can be deduced from this figure. So how do we understand this? The value of macroscopic shear strain is related to the number of dislocations within the crystal and the degree to which each of them has slipped. So the total strain stored in the material has something to do with what each individual dislocation experience inside the crystal. That is the message, the bottom line. Okay. So the macroscopic shear strain is gamma is equal to delta by h. This is straightforward from this displacement by the height, where h is the crystal height and delta is the displacement of the top crystal plane relative to the bottom one, because it is a pure shear. This displacement is sum of the displacements of individual dislocations, that is delta is equal to summation over delta I, where delta I represents an individual dislocation displacement. Okay, very important. And it also gives a perspective why we study the dislocation nature in terms of what material response it produces. Right? The later is given as what is later here? The individual dislocation displacement is given as xi divided by L whole divided by B, where xi is the distance from the left side of the crystal of the dislocation I, and L is the slip plane length. So, okay, this is for an individual dislocations. So this we know. Hence, x by L is the fractional displacement of the dislocation on the slip plane. When this is unity, the dislocation has produced a slip offset equal to the Burger's vector. Thus, we can write a shear strain is equal to B by LH. What is B by LH? We are taking these things from this total macroscopic shear, and then we are substituting with individual displacement. So B by LH times summation over xi, which is equal to B by LH n x bar, where n is the total number of dislocations and x bar is the average dislocation displacement on the slip planes. The dislocation density rho is given as nz by LZH. okay, where Z is the crystal width. Thus, we see that the gamma, the macroscopic shear strain, is equal to rho V x bar. Okay, this is one important expression relating the dislocation density with macroscopic shear strain. So the above equation relates the shear strain to the dislocation population and the extent to which the average dislocation has slipped. Okay. And then differentiation of this equation with respect to the time leads to a relationship between a shear strain and an average dislocation velocity. V bar is equal to dx bar by dt. This is again an interesting aspect. If the dislocation population is constant, then we can write that gamma is a shear rate, right? Rate gamma dot is equal to, this is not P, this is rho. This is a typo here. Rho V V bar. So this is a shear rate is related to the dislocation velocity. Okay, this is again a very interesting point to note. So what we have now looked at is the equations that are appropriate to the total dislocation density provided x bar and v bar are measured relative to this population. So all these equations are valid for a total dislocation density. It's not pertaining to any particular type of dislocation or something like that. It is a macroscopic strain. Just to give you an idea of why what is the connection between the dislocation density and the macroscopic strain. That is another fundamental aspect. That's why I wanted to discuss this. And finally, I want to introduce another interesting parameter, lattice resistance to dislocation moment. So the Peierls stress. So we have studied now what are the forces on dislocation, or what is the stress field around dislocation. Okay, what is the minimum force that is required to move a dislocation inside the crystal? Suppose if you have one just dislocation sitting in the perfect crystal, how much energy is required to move them, or how much stress is required to move them in a lattice? This is of very primary importance conceptually, not quantified for any systems, but conceptually it is very important parameter. So I thought you should know this before we talk about dislocation motion and hardening, etc. The force necessary to move dislocation through the lattice when no other impediments to the dislocation motion are present. An important characteristic of this force, called Peierls-Nabarro or Peierls force, is that its magnitude varies periodically as the dislocation moves through the lattice. So that means the Peierls stress is not going to be a constant factor. It is going to vary, and it's going to be very different depending upon the characteristic of a material. That is what it means. So look at this schematic. It's very interesting schematic. What is shown here is a characteristic width of an edge dislocation that affects the Peierls-Nabarro stress. Characteristic width. What is this characteristic width? So this is a lattice, and these are all bonds which is continuing from the top, and this is bottom. This is a lattice parameter A, and something I have marked here as W, and a similar thing where I have written wide, and this W is narrow. So what is W? let us try to understand that first. So the extra half plane is inserted here, and because of that, there is a disturbance in the interatomic spacing in the neighborhood. Okay. So if you look at this, this is straight bond, this is straight, this is straight. It started going inclined fashion, inclined, inclined, inclined. So suppose if the extra half plane is inserted here, how much distortion it creates, or how far the distortion is going through. So that is the measure of the W. Okay. Because of this edge dislocation got inserted, how much disturbance it creates on both sides of the lattice. Okay. This is for a single dislocation, because we are interested in studying this Peierls stress, moving this dislocation. So that means if you look at this figure, if you look at the bond here, they are all straight, but it started it starts distorting only from this point. So that is the W here. So compared to this and this is a narrow width, this is a wider width. So what does it mean? It means it is going to be a characteristic of a material how it is going to distort its lattice in the presence of any dislocation. Okay. So indirectly, what is that we are saying? We are saying how much is the bond strength or the resistant force. Now we go back to our fundamental idea, right? The bond strength, the restoring force, the resisting force, right? Suppose if you insert the dislocation, how much it resists, or how much it is allowing, or how much it is responding indirectly. That is one way of looking at it, right? So this is going to decide the stress required or a force required to move a dislocation in the lattice. Okay, so the characteristic width is going to decide. So how it is going to decide? It is known that the magnitude of the Peierls stress or a lattice friction depends to a large extent on one, the width of the dislocation W, which represent the measure of distance over which the lattice is distorted because of the presence of the dislocation, and the distance between the similar planes, that is lattice parameter. The Peierls stress has been shown to depend on W and V in the form tau Peierls-Nabarro, that is for Pm, proportional to G into exponential minus 2 pi W by B, where the W is A divided by 1 minus nu. 1 minus nu, you know, it is because edge dislocation, right? From the above equation, the Peierls stress for a given plane is seen to decrease with increasing distance between like planes. Okay. Since the distance between the planes varies inversely with their atomic density, slip is preferred on a closely packed planes. These are all very fundamental ideas which gives us much more perspective about this concept. In addition, Peierls stress depends on the dislocation width, which is dependent on atomic structure and the nature of atomic bonding forces. So now we are coming to a very fundamental idea, bonding forces. That is how we started this course. Now, where do we stand now? We are now talking about the force required to move a dislocation in a lattice is strongly connected to atomic bonding. Okay. Bonding forces. For example, when the bonding forces are spherical in distribution and act along the line of centers between the atoms, the dislocation width is large. So what does it mean? Your bonding should not be directional in nature. The bonding should be spherical. That means something like you have electron cloud in the metals, right? It is spherical around all the atoms. It is not like ionic and covalent bond, which are highly directional. Right? So in these kind of situations, the Peierls stress will be smaller. Very important idea. Very important and nice idea. Since this type of bonding is found in close packed structures, it is seen that Peierls stress in FCC and HCP crystal is low. Okay. By contrast, when bonding forces are highly directional, as in the case of covalent ionic and BCC crystals, the dislocation width is narrow and the Peierls stress correspondingly large. Very sharp connection between the deformation, the very basic deformation characteristics and its bonding nature. Right? Very important. It is difficult to measure a precise force displacement curve for this Peierls stress experiment. Hence, the Peierls stress in crystals can be described only in qualitative terms. It is only a qualitative term, not a quantitative so far. How about temperature effect? The Peierls stress temperature sensitivity. Since the Peierls stress depends on the short range stress field of dislocation core, it is sensitive to the thermal energy in the lattice and hence the test temperature. Okay. At low temperature, where thermal enhancement of dislocation motion is limited, the Peierls stress is larger than at high temperature. In crystals that have wide dislocations, however, the increase in Peierls stress with the decreasing temperature is insignificant, since the Peierls stress is negligible to begin with for materials which is having wide dislocations. Accordingly, there is a little yield strength temperature dependence in FCC metals such as aluminum, copper, and austenitic stainless steels. You see, it has got immediate correlations. We talk about wide dislocation. Which of the material will have wide dislocation? Typically, the material which possess are metals which possess FCC crystal stress system, like aluminum and copper and austenitic stainless steel. They all will have very wide dislocation, dislocation length, W. The length of the W is quite large in this material, and they don't have the much temperature dependence, Peierls stress. On the other hand, if you look at this table, it's quite interesting. The relationship between dislocation width and yield strength temperature sensitivity. You take a material, metal, crystal type FCC, dislocation width wide, Peierls stress very small, yield strength temperature sensitivity is negligible. If you take a metal of BCC type, dislocation width is narrow, Peierls stress is moderate, and temperature sensitivity is strong. So even within this metals, if it is BCC FCC, there is a huge difference in the Peierls stress. So it's very small, here it's moderate, and temperature sensitivity negligible, and here it becomes strong again. Okay. Coming to ceramic, and if it is of ionic type, the dislocation width is going to be narrow and the Peierls stress is large. Very interesting and important point. And the yield strength temperature sensitivity is also very, very high. And if you take ceramic, which is of covalently bonded, will have very narrow dislocation width, and will have very large Peierls stress and a very strong yield temperature sensitivity. So what does it say? In crystals that contain narrow dislocation, although the Peierls stress in the materials may be small at elevated temperature, it rises rapidly with decreasing temperature and represents a large component of the yield strength in the low temperature regime. This can manifest itself as an increase in the elastic limit, an increase in the hardness, and a decrease in ductility. So now you can quickly connect these characteristics to the ceramic, right? Okay. Very high elastic modulus, very high hardness, very poor ductility. Right? So the large Peierls stress in ceramics material is partly responsible for their limited ductility at low and moderate temperatures. Okay. So the Peierls stress decreases rapidly with increasing temperature, thereby enhancing the plastic deformation processes in these materials at high temperatures. So this is about a material which is having ionic and covalent bonds. The Peierls stress decreases rapidly with increasing temperature. So I think I have given you some prospects of dislocation and its various characteristics, how it is going to influence the material behavior. Okay, I think this forms a good background for proceeding further into this, the core ideas of mechanical behavior of materials. So from the next class, I will get into the main ideas, main syllabus, I would say. I will go to the plastic deformation. I will start with the plasticity theory principles, very basic ideas. And then we will proceed with the deformation characteristic of different kinds of materials. So what we have looked at in all these lectures so far is we have, in principle, I just took it as, what all can be covered in a theory of elasticity, where all it has been used and how it describes. So that's how we looked at elastic stress-strain relations, elastic properties, and then anelasticity and description of dislocations and all this, domains. The theory of elasticity has contributed immensely in explaining all this behavior. So that is kind of a full domain we have covered, and also it formed a very good starting point and background for the rest of the course. So from next class onwards, we will deal with the plastic deformation, and we will start with the basic plasticity theory. Thank you.